You ready for me, Pete? Yeah? That's good. Okay, everybody. Welcome back. Thanks for coming on the IROS deadline. So I want to pick up where we left off. We told you last time we did the swing up control for the acrobat and the cart pole, but I tried to do it with some insights that came from Lyapunov functions, and I want to really continue that story and start understanding the computational implications of thinking about Lyapunov functions, for instance, versus dynamic programming. And I mentioned the relationship last time, of course, but there's some deeper computational implications about that difference that I want to try to highlight today. I'll show you how you can find Lyapunov functions with linear programming, and just make sure you know what linear programming is. Pete has been telling me, he says, if you come by my lab anytime, then you're very likely, if you stay for more than 5 minutes, you'll hear something about convex optimization this, or linear program, or semi-definite program that, or whatever. It's the thing, it's the vocabulary of the lab. And Pete says, Russ, you haven't dropped the hammer yet. We got to start using convex optimization in Underactuated. So I promised him at least. I don't want it to drop like a hammer, but I do want to start using it as part of the vocabulary of the class, because it really is central in the way I think about these problems now. And I'll at least, depending on the time, I'll make at least a call out to some really, one of the big things that's nice about Lyapunov analysis is that it can capture some of the ideas of robustness that we saw just anecdotally in the controllers that we talked about last time. But we'll see now mechanically, how we can algorithmically approach the question of robustness with the language of Lyapunov. Okay, so let's start by just putting dynamic programming and Lyapunov analysis sort of right head to head here. Versus okay, so as they've been introduced so far, although this is not a completely perfect distinction, but dynamic programming is doing more than what we did with Lyapunov analysis so far. This is trying to find an optimal controller. Right? But it also gave us a language for certifying optimality. Lyapunov analysis is doing a little less, but something very important, right? It's just trying to certify stability. And you could say stability of what? You can have stability of your cost, and there's ways to connect those two and make them more and more similar. But But the equations and the mechanisms are very similar with just a few key differences that I really want to pull across. So I've never tried this before, but today I want to try doing it actually in the discrete state and discrete action, because I just think it's so simple there. It's really nice to think about it. So back to the discrete version of this, if we set our dynamics are governed by that equation. In the Lyapunov case, we didn't even talk about the action space. We just said we had a closed loop system here, right? You could imagine that equivalently being, if I have some controller, then it's f of Sn, and pi of Sn, for instance, stuck into my actions. If I, want to relate the two. I wanted to just say that the actions here were drawn from some function of state, my controller, then I could have written it like this, right? And it's exactly back to what we were using in Lyapunov analysis. The idea here was that we could write the cost to go function recursively. So then the idea here, which I said, I only said it in continuous time last time, but I think hopefully the idea transfers so easily conceptually that it won't be surprising to, so the idea was that you go downhill, right, on V over time. So in the continuous time, I said that V dot should be less than or equal to 0, where V dot was partial V, partial X. This is what I wrote last time. So what is the analog in discrete state actions, everything? You just want to say that V of Sn plus 1 had better be less than V at Sn. Right? You just want to be going downhill on some function V. And to make it look a little bit more like this, can I just flip that around and say V of S is greater than equal to V of F of S. Okay, so, oh, sorry, yeah, that's right. They appear now in the same places. Okay. And now there's a couple key differences. This one's got a min, this one's got a G, this one's got an A. Those are some big differences, but actually, maybe the biggest difference of all is that this one's got an equality and this one's got an inequality. And we're going to see that that opening the door to having inequality only hold is going to enable us to use simpler functions to describe complex things. Okay? All right, so let's dig in and sort of look at those differences a little bit more carefully. So, on the face of it, and probably admittedly, the biggest difference really is that this is trying to find a controller, and that one's just trying to verify a controller. It's almost an unfair advantage for Lyapunov to say someone's going to give me the controller, I don't even have to find it. So what's the corresponding problem in dynamic programming that's a sort of more apples to apples comparison? In dynamic programming, if controller is given, then there's still a problem that uses those equations. It's called policy evaluation. where you'd like to quickly assess what's the cost to go, what's the cost that I should expect to receive if I'm executing this controller over time. And that's the very analogous question with stability, right? If my cost is going to be infinite, then I'm probably not going to get to the goal, right? And you can make those connections deep, right? So, if J pi of S is our long-term cost now, that's the definition of the cost of executing this policy from initial state S for the infinite horizon, in the infinite horizon case. Then, looking at that equation, you can see the same sort of recursion holds. It's just that the policy is given. So you can still write that as J pi of S is now G of S. And you can write the A's or not, but I'm going to just leave them off to keep my hand fresh. Okay? If I can solve this equation for J, or if I can find a J that satisfies this equation, then I've understood the cost to go of executing policy pi from state S. Right? Okay, so let's think about in the case of discrete states and discrete actions, remember, I actually, this is just a number for every discrete state. So I can replace that with a vector, and this is just a cost for every discrete state. And this is, again, a vector. So I can rewrite that whole thing as a vector J pi, right? Where the ith element of the vector is the J of Si, right? Is some vector G. And how are we going to write that? That's some transition matrix times the vector J again, where this thing Tij is 1 if f of Sj, right? If Sj is f of Si. Because you want the next one, yeah. 0 otherwise. I wrote I twice. I said it right. Yeah. Like J's curved backwards. I'm so proud of saying it right that I wrote it wrong. Okay, so this is just an equivalent version of that in the special case where J is discrete, takes discrete values at discrete locations. What's amazing about that equation? That's just a linear equation, right? So I can solve that in closed form for J, right? So, you could write I minus T J hat equals G. You can invert that. More generally, whether this is invertible or not is put some requirements on T. But more generally, I can try to find a solution J this is, you think of this as now a linear equation, ax equals b, and I'm trying to find the x, right? So there's this whole world of how to do that, depending on if A is full rank or what size A is, right? And they all come down to the pseudo-inverse idea is just you try to, in this form, minimize x of ax minus b in some, squared. People know this? I'm going to turn around and look in a second. People know how to get the pseudo-inverse and how the general form of that is? It's actually pretty similar to what we're going to do in a second, and it's 3 lines, so I'll just do it real quick. So this thing, if you carried it out, that's it's got this looks like X transpose A X minus I want B transpose AX plus some constant that doesn't matter. And since this thing is positive definite, I can take the gradient of that in my notation from the other day. If I take the gradient of that whole thing with respect to x, right? That's just a quadratic function of x that has a minimum somewhere. So I'm going to find the minimum by just looking where the gradient vanishes. Since A times A transpose is something squared, I know that's going to be a positive objective. So I'm going to take the gradient of that. I should have put a half here. Can I put a half back in there? Is that too late? That way that I didn't miss a 2 here and I'm going all good. Then I get A transpose AX minus B transpose A. And I want this, find out where that equals 0. So I get AX equals my sort of inverse A transpose B. Right, that's the optimal X, and that's the least square solution to any problem like this. So if you insert this here, that there, then this gives you a formula that robustly solves for the vector J. That should be sort of surprising. I mean, the math's not surprising, but the fact that I can just, boom, one shot compute the cost to go of any policy on for any controller, admittedly discrete, just bam, solve a set of linear equations, and I know how it performs from every initial condition. That's pretty good, right? The cool thing is, this also works in the case of function approximators. Okay, so now we're going to start getting away from remember the steps we took to get away from S to more continuous X? The first step we said was, let's just even if we had a discrete set of states, but there's just a lot of them, and I didn't want to have to solve for J at every point. I could solve for some feature-based approximator of that. With linear function approximation. If I said that J of S hat is some, just some linear combination of some features of my vector of my state S, where these are my coefficients. I'm going to try to find, and these are my fixed basis functions. Cool thing is I can do exactly the same thing right here. If I were to just put in now alpha transpose phi of S equals G, maybe we have to do this. This is a vector for every possible S, equals G plus T alpha transpose phi of S. Okay. I could shove the T around if I need to, but this is still linear in alpha. So it still looks like AX equals B, and I can solve for the least square solution to my cost to go by just solving a set of least linear equations, right? So that's very cool, and I can do that also in continuous state, right? If that's now at a bunch of sample points, I could still do this if it's now j hat pi x, right? And now I try to minimize this at a bunch of sample points. Minimize j minus g tj at sample points xi. That's awesome. Yeah?
Is phi always linear?
Is what?
Phi always linear?
Phi can be as nonlinear as you want. The thing you can't do is stick your decision variables inside it. Sines, cosines, whatever, have a field day with phi, but keep these guys outside for this result. Okay, so you give me an arbitrary controller, I can then just solve a set of linear equations at a bunch of sample points and find the best least squares fit to the cost to go. So why doesn't that solve the problem? Like, why aren't we done? Why are we doing this all the time, forever? Okay, so now, especially in this case, where, even in this case, as soon as you've introduced function approximation, the solution to this equation is not going to be 0, right? You're not going to fit it exactly. You're going to have some errors. Given that you've got some errors, what can you say about how well your controller is going to work? Right? It's frustrating, but you really can't say anything, okay? As soon as you've got some errors there, because this is minimizing a least squares objective on the sort of recurrence relation, it's trying to match itself relative, at each point it's trying to match its neighbors. That's all good. Okay, but small errors in all your neighbors can build up. Like you saw that in the double integrator, right? That eventually, everything looks self-consistent, everything's good, but actually the curve missed the optimal curve by increasing amount as you go farther away, right? Those small differences in the solution sort of integrate backwards over time, over state in this case, and mean that having even a low error but non-zero error in sort of this fit does not tell you anything about how well you've actually captured this long-term cost.
But for the discrete case, we solve it exactly.
So in the discrete case where j is a vector for every state, it's solved exactly. Yeah. It's only the problem in the case where you've used function approximators. So it's to the point where I actually can't tell you if the pendulum's going to swing up or swing down or whatever. I can sort of say, it looks good, the cost is kind of small, but there's really no guarantees anymore whatsoever about what's the long-term performance of the system going to do. It could be that small errors in my cost to go can build up over state to the point where it's changed the direction that my system is going to go, and my controller is actually going to fail. Yeah?
Can you have to make sure that the errors gives the right sign?
Good. So, did you hear the proposal? The proposal was, can we make sure that the errors have the right sign? And the reason that that's clearly the right thing to do is because of Lyapunov, right? So that's exactly the right thing to do. Well, it's actually having the errors of this equation have the right sign is fine. That could give you a bound on the cost. But if you just want to know whether you're going to get to the goal, all you have to make sure is that you satisfy that equation also. Right? So if you can find a solution that's a pretty good fit to the cost to go, but also has the stronger property that whenever I move along my dynamics, I'm going to go downhill, then you have a stronger statement, right? About something, you can say something about the long-term stability. here, we would like J hat I to also have that property. If you can certify that for all S, now I'm going to gloss over for today the idea of certifying it for all continuous X. That's possible. It's a little bit harder, but that'll be next Tuesday. But certifying it for all S is something that we can certainly do. And if you have that property, you find let's say the least square solution that is also subject to this constraint, then you can start saying something like, well, that's also a Lyapunov function, and I can then talk about with all the subtleties of Lyapunov analysis, right? If it's only less than or equal to 0, then I have something about stability in the sense of invariance, but not in the sense of convergence, right? And all those details. Actually, maybe it's worth even saying. So you remember that the subtlety, if we said v dot of x was less than or equal to 0, this was stability sort of in the sense of Lyapunov. And then we said v dot strictly less than 0 away from 0 is asymptotic stability. And then v dot somehow less than some constant, potentially small constant of v would give me exponential stability. So in a way, I think the intuition you could have, it would be to connect these ideas to your intuition for cost to goes and cost functions in dynamic programming, right? So if I really just set my cost to be 0 everywhere, then and I verify that my cost to go has some property, and matching my cost instantaneously does not tell me I'm going to get to the goal if the cost was just 0 everywhere. That's sort of everywhere the cost was 0. If there's a plateau where the cost was 0, and I'm saying that J equals the one-step cost is my cost to go decrease, I could be anywhere in that 0 cost landscape as time goes to infinity. If you want to converge, then you need, this is sort of like, I'm a little hand wavy, this is more for your intuition than for the theory, but this is sort of like G of S equaling 0. Asymptotic stability is sort of like G of S is some small number apart from when you're at the origin, maybe. You just want to make sure you're going there with some, eventually. And then the exponential is sort of like G of S is bounded by some, it's like bigger than some quadratic function. So it's got some rate that it'll go down. Okay? So to some extent, I think the intuition you have about cost to goes should really map nicely to what you can say about Lyapunov. I don't really like writing that, but. Okay, but so we agree, I think, that if we can just add these extra constraints to make sure the error is bounded on one side, then we'd be happier with our ability to say something about the system. But that breaks this machinery, right? I had a nice quadratic optimization. I just found the gradient equal to 0, and I've got a solution. What happens if I've thrown in some additional constraints into this question? Okay, then I don't have this recipe doesn't follow. It changes from a least squares optimization problem into a linear program, or a quadratic program if I keep this objective, right? So that's the hammer is hanging above us at this point here. asked once before, but how many people know linear programming, quadratic programming, and the like? Nice, okay. So I mean, there's great texts, and I can't give you the full course on it. So I was only planning to do sort of the high-level idea, but the optimization that we end up with here becomes depending on if we keep our original goal of matching the cost to go, or if we really just go to the Lyapunov question. If we really just want to write this, find some vector alpha such that, let's say, for all xi, my j of xi hat pi is, which way did I write it? And that looks very similar. The structure of that optimization problem is of the form, find b and x subject to the constraints that a of x is less than or equal to b. And this is called a linear program, or it's the stuff of linear programming. Okay, so I feel duty bound to just spend a few minutes saying what convex optimization is. Okay, right. So the general form of optimization problems that we've seen a lot of times in the class, and we will continue to see much more in the class. I want to try to minimize some function of x subject to some constraints, g of x I less than or equal to 0, where these are decision variables this is my objective. These are my constraints. And I have potentially many of them. Okay, so then the problem is basically what we looked at before, right? It's you've got some function f of x. You're trying to find the minimum of it as a function of x. You might have constraints which say, okay, yes, I want the minimum, but I only want the minimum, where did I put my chart? In some particular states. Like I care about the ones that are in this interval, and those would be my constraints. Let's say g1 of x is greater than or is less than equal to 0 there, and g2 of x less than equal to 0 here. That's not true. Let's keep it also g1 of x. All right. Then the answer would be I'm going to find the smallest point. I drew it, so it's either this one or this one. I don't know. It's one of those two, right? But it's not necessarily the smallest point on f. It's restricted to some domain. And the big idea that I want to make sure you realize is that not all optimizations are created equal. Functions that look like this which are convex, defined rigorously as for any two points, the line segment between them is strictly above the function. Right. So if I take x1 and x2, then I'd like I'd like this line segment, which I can say this is f of x1 plus f of x2, but I'm going to take a linear combination, alpha of this, 1 minus alpha of this, for, okay, that would be the value here, and this thing had better be greater than or equal to whatever the actual function is at that point. Okay, if I have a convex function, that seems like an easier one to find the minimum of course. Okay? Same thing's true, the constraints matter too, the shape of the constraints. If I have totally bizarre constraints, then I might have to look over here and over here and over here. And life is way better if the constraints are convex, for themselves form a convex set. Okay, so if I have now x1 and x2, then I can have many different constraints, but the region that they describe, the place that satisfies all the constraints, had better have the property that any 2 points that are inside that set, there's a line segment that connects them, which is also entirely contained inside the set. Okay? And, so a non-convex set might look like this, where if there's points like here, then the line segment leaves the set. Okay, and the intuition should be, I think, pretty straightforward, even if you haven't thought a lot about this. But if I'm going to just try to find the minimum of that solution, then if there's no local minima, then it's easier. Similarly, since I'm going to be doing it on some set, even if I had a convex function, but I was going downhill and I got stuck here on the wall where there's a pit before I come back and there's another solution over here that would have been better, then having a non-convex set of constraints also makes the problem much harder. If I'm in a convex function and a convex set with convex constraints, then the optimization problem is much easier for numerical methods, and that's the stuff of convex optimization. There are some great courses here on it, and I would recommend them really. I think it's a very, very powerful set of tools. There's a great book by Steve Boyd and Vandenberg. So Stanford, called Convex Optimization. The PDF is online. It's the best reference I can give you to all this stuff. Okay, so I would actually say in our lab, for instance, one of the things we spend a lot of time on is trying to find clever ways to take problems that are generated by, let's say, Newton, or whoever gave us the problem, or the machine shop or something like this. We've got a problem in front of us, and the equations look like this. Okay, when they come out of the bag, they look like this, and they're hard to optimize, and we don't have a lot to do with them. And maybe by massaging them, by changing coordinates, whatever, we can make them look more like this. And it's sometimes surprising how far you can go, where you can take, there's a lot of structure in the equations of motion of robots, for instance, that will allow you to write pretty powerful convex optimizations to solve pretty hard control problems. So it's a really important idea. Okay, so then the two that we're sort of introduced here, the two special cases of convex optimization are linear programming which is minimized over x, C transpose x, subject to AX less than or equal to B. Or if we wanted to put our objective back in to match the cost to go function, the one-step cost to go function everywhere, while also satisfying these constraints, then we get a quadratic program, which looks like minimum of x transpose qx plus, let's see, E transpose x not B, let's do C. Subject to AX less than or equal to B. Okay? In practice, what it means is if you can find a way to write your problem down, okay, if you can write it down like this without the constraints, then it's got a closed form solution and you're doing least squares, and that's the best case. Okay? But you can write down very big programs, with high dimensional X and many constraints, and hand them to a commercial solver and expect very fast, reliable convergence to a global optima for problems that look like this. So these days, getting your problem into a form that looks like one of these is sort of tantamount to solving the problem. It's not quite as satisfying, but it's really good. In practice, when Atlas, our 400-pound humanoid robot, is walking around and balancing, it is solving quadratic programs at a kilohertz in order to balance, right? Every once in a while, the solver gets slow and the robot falls down. But most of the time, it's really good, and it's a perfectly good way to robot. We actually, there's a long story about that, but it's basically true. Okay, so does that make sense then that we've taken the Lyapunov, we've taken the HJB equations and observed that fitting them in a least squares sense, which is all you're going to be able to do in continuous space or in high dimensions, you're not going to be able to get a perfect representation to numerical precision of your true cost to go function. You're going to be doing some approximation. Once you do any approximation, if you've just tried to match your Hamilton-Jacobi equation everywhere, you have no guarantees about how the system's going to work. If you throw on a little Lyapunov constraint, which is an inequality constraint, then you can say something strong. But what I really want to point out is the power of actually of that constraint, right? So the difference between that equality and the inequality, right? We just do a head-to-head comparison between solving this problem versus finding some V there's a big difference in trying to ask about matching this exactly and saying that I want my function in continuous time, all these things hold, all my analogies hold, by the way, right? So in continuous time, it was min over u, but in the no cost, or in the controller given case, it would just be partial j partial x f of x versus v dot. So the big difference here is the equality constraint versus the inequality constraint. And the point that I want to make is that, and it makes a huge difference, finding the true j is very hard. In general, it means solving the partial differential equations. Finding v's, in this case, we had to go to linear programming, so it felt like a harder numerical problem. But many more v's can satisfy these equations than there's a single sort of, in most cases, a unique solution to j, but many v's can satisfy these equations. For instance, if you found one v you liked, multiply it by 2. You got another one that works too, right? Add 5 to it, that works. So there's many more functions that are going to satisfy those equations. In practice, what we're going to look at, when we try to solve, for instance, even if I take the value iteration solution you've been thinking about for the pendulum swinging up, think about how you'd write that with simple functions, right? If you didn't have a mesh that could cover that whole state space, you had to cover it with simple functions, with a few sines and cosines. It's very hard. I've actually spent some time trying, and I haven't found a good small set of functions that can do any reasonable job of fitting the cost to go. But you can find functions that'll satisfy this. We did it last time. In fact, that was sort of the energy shaping idea, right? Exploited this, right? And the view I gave you of nonlinear control exploited this. It was really like, it started with mechanical intuition. Of using energy to stabilize the homoclinic orbit. But then it was sort of, let's take a few sines here, a few cosines here. It was a little bit of algebra mishmash to just find any function that satisfied that equation. If it was really hard to satisfy that equation, like this one, you wouldn't have been able to sort of get lucky and find it, pull a few rabbits out of the hat and find it. But then, you could sort of, that was a human search, right? Sine, cos, whatever, until they satisfied those conditions. In practice, we're going to see convex optimization, for instance, is going to go farther with Lyapunov analysis than with optimal control. Because I can write down fairly simple functions that describe the behavior of complex systems that satisfy these equations but don't match these very well. Okay? In fact, here, let me give you, I thought about bringing the laptop. Let me actually, I'll push this in the notes, but let me tell you about a very satisfying example that that you should run as soon as I push it to the textbook. But I stayed up all night working on it, and then it runs, and then it prints out 4 numbers, and then it wasn't compiled on my machine at work in time. So I was like, printing out 4 numbers is not worth the stress. But you should run it for yourself and see those 4 numbers because they're really good. I admit that the problem's goals are modest again, but the fact that that this works is awesome. Okay, so. Proving global asymptotic stability of a damped pendulum, sorry. And let me just go into the mechanics of how you set that up. Because the really cool thing is this optimization, you give it a bunch of phi's, like a set of basis functions that has some sines, has some cosines, maybe a theta dot, okay? You ask it to find the coefficients that satisfy the Lyapunov equations, and you know what comes out? Mechanical energy. Not actually mechanical energy. Mechanical energy plus a little term, because mechanical energy had that problem. It didn't actually prove asymptotic stability. Because anytime theta dot went to 0, it was exactly, v dot was 0, not less than 0. Turns out there's something a little better than mechanical energy for the damped system, which has a little theta dot squared term put in, and it reconstructs that. So the coefficients that come out are mechanical energy plus, oh, here's that thing that you didn't remember to write on the board, and it makes the proof actually that you'll converge. There's some subtlety though, because it doesn't converge global asymptotically except for a set of measure 0, right? There's some states where it doesn't converge because there's another fixed point at the top. So how do you write all that down? So f of x is just the pendulum dynamics. I used phi of x. I tried not to cheat, but so in my world, this is just the vector of monomials. And I'll tell you what that means. But basically, I put in 1 sine theta, cos theta, theta dot, and then every combination of those that had only order up to 2. So sine squared theta. I didn't actually write cosine squared theta because that's already included from 1 minus sine squared theta. But I had sine theta cos theta, theta dot sine theta, theta dot cos theta, theta dot squared. Okay. So the task of the optimizer is, find the coefficients for each of these to build a V. Find alpha, right? And if it does what I just claimed it does, then it finds ml squared, theta dot, squared, and the like, and it's awesome. Okay. Then how do you write the constraints? Well, so this, by the way, this is the way I would call this. This is all monomials, because it's a polynomial in sine, cosine, and theta dot. So this is monomials of sine, cosine, and theta dot for degree between 0 and 2. When you see the code, that's what it means. It's take all multiplicative combinations of these for your features. Okay, so then I said, find me an alpha such that for all xi at samples xi, v of xi is greater than or equal to some epsilon xi squared, roughly. I'm trying to prove that the origin is stable. So I'm going to say I'd like v to go up away from it. If I just set this to 0, then it could have come back with a flat v, and it wouldn't have proven asymptotic stability. Okay, and then I said v dot of xi, which of course is partial v partial x, f of x. That had to be less than or equal to some epsilon xi transpose xi. And here's the trick, really, times sine squared theta. So I want v dot to be always going down, but I admit that there's, that at the upright, it's going to have to be 0. So I'm going to allow that to happen by thumping it, basically driving that thing, allowing that thing to be exactly identically 0 at the upright. Okay, so sine was my arbitrary choice to just make sure that that objective went to 0 there. And then I said v0 equals 0. V dot 0 is trivially 0 at the origin because it's a fixed point. You send that to an LP solver. A Roby, in my case, is a commercial solver. That's the other thing we have to figure out, is how to make sure you guys have a solver that works for this. And the thing that kicks out is the coefficients of this look numerically very close to being the mechanical energy of the system. And you change mass, you change length, whatever, you run it again, and you get it. It figures out the energy. Right? That's satisfying. That's really satisfying. The only thing that's not satisfying about this, in my mind, is having to do it for a lot of x and only having the guarantee hold at a bunch of sample points. So we're gonna do that better next week, because there is a more complicated optimization that will do that better. It's instead of a linear program, it's going to be a semi-definite program, and it's going to use sums of squares optimization. But the only thing it accomplishes over this, in fact, the formulation is identical. Almost, I do have a version of this in sums of squares that uses sines and cosines, and the version is almost identical. The capability it adds is the ability to do for all x, and that's a fundamental capability because sampling works in low dimensions, but if you start going to high dimensions, then you're going to be dead in the water. Okay, questions about that? Oh, good.
What were the 4 numbers? The basis function is really big, so alpha is probably also not 4.
Sorry, so I have, this is alpha 0, alpha 1, alpha 2, alpha 3. There's a coefficient for every one of those. And the coefficient of this was ml squared.
Oh, cool.
And the coefficient of this was mgl. And there was a coefficient of, I forget what the other one was that made it, I think it was,
Zeros?
what's that?
Were the rest zeros?
The rest were close to 0, yeah. And that's subtle because the way, I didn't put an objective on this. When I write find alpha, that's called a feasibility problem instead of an optimization problem. I didn't actually put an objective. So the only reason that those go to the zeros is actually just because the solver tends to drive things towards 0 if you have interior point solvers and the like. But that's right. It should satisfy the conditions regardless. The fact that it chose of the many candidates the one near 0 is just a feature of the solvers. Yes?
A simple question to that. In your statement of the linear programming, why are you minimizing C transpose X?
That's that's the general form of any linear program. And in the particular case of us, we could, I would actually have just left C to all zeros if I just wanted to write this, which is what I did there. And alternatively, if I were to write a quadratic programming form that I could say, find the V that matches this function as well as you can, but also satisfies all those constraints. There are some ideas that you could put in that would have linear objectives that would try to do a better job of this. So, okay, this actually gets to a subtlety that I think is worth getting to. So, the fact that this can be satisfied by many, many equations can also get you into trouble. For instance, your optimization is technically unbounded. I mean, you could have your coefficients go off to infinity and they would still be satisfying these equations. Sometimes solvers get mad at you when you do that. The linear programming and quadratic programming solvers, they're strong, they're good, they're mature, and they say, that guy doesn't know what he's asking for, I'll clean it up and I'll solve the real problem. And the SDP solvers, when we start using them, they're just going to fall down to their knees and cry and say, I have numerical errors, you're going to have to ask me a different question. So that can really matter. So a lot of times you end up adding, so the trick of adding V0 equals 0, for instance, that mattered. But if I actually had too many coefficients in here, I could get myself into trouble again, because it could, a lot of times I'll put boundary conditions. If I don't actually know what shape V should be, I mean, I could have one that's very steep, very shallow. They both are going downhill if they have the right shape, right? So sometimes I will do things like arbitrarily saying the origin is 0 and this point over here is 1. And that sort of sets a boundary condition that makes the problem well defined everywhere and improves the numerics everywhere, because it doesn't try to find some big numbers that satisfy the equations. If you had a mesh representation, then putting a point over here to say equal to 1 would not be enough to constrain the boundary over there. So there's all kinds of details that start coming in when you really start playing with it. I'm sorry you had your hand up so long.
Is there a good reason for the optimization finds mechanical energy as opposed to 2 times mechanical energy?
I think it actually is. It's a constant times the true mechanical energy. Yeah, I took that constant out for effect. Maybe that's the truth of why I didn't bring the number or bring the laptop. But yeah, that's a good question. Okay, one more super key idea that I want to get across today, and that's the idea that. Do you remember what we said about the energy shaping controllers are actually better than a lot of the optimal controllers we've been doing, because they were somehow, going to the homoclinic orbit, and the homoclinic orbit is not defined in terms of mass at all, right? It's very robust to the parameters. Your controller is just theta dot times E tilde, and that controller doesn't depend on the mass. I admit it depends on the length, but that should be easy to get right. It's a very, very robust controller. And so far in optimal control, we haven't had the language to talk about. We can add the language in many ways, but a very easy way to add the language for saying let's be robust against model uncertainty is available in the world of Lyapunov. Okay? So let's do that. So how did, think for a minute about, you've got a robot, you know that the right wheel turns a little differently than the left wheel, and if I just send a constant current, it would sort of veer to the left, right? So what does that mean when you're writing equations and trying to optimize, right? So how does that manifest? A lot of times, the sort of robust control theory of how you do that, you would often put bounded uncertainty, this is not the only way, but this is just one powerful way, bounded uncertainty on the parameters of your system. So you could say, for instance, the friction in my wheel is between 10 and 12. or the mass of my pendulum is between 1 kilogram and 2 kilograms, and I don't really know what it is, but I'd like to find a controller that works for all systems that have mass between 1 and 2 kilograms. Right? So competing idea, which we won't use right now, but we will later in the class, but just so you have the context for it, the competing idea would be to put some probability distribution over the models, right? So you'd say that my mass is drawn from a Gaussian, let's say, that is centered at 1. And there's those terms can often be pushed through. Sometimes they're not as elegant. We can push these through the stochastic equivalent of these optimization problems. But the bounded uncertainty just snaps right into what we said right now. It's still a linear program. It's all good. Okay? So the simplest way, I think, to tell you is imagine in the discrete, since I wrote the equations with discrete state, discrete action, discrete time. The discrete equivalent of the bounded uncertainty would be that, let's say I have S of n plus 1 is sort of, it could be F1 Sn. Yeah, let me even just not worry about that again right now. We're doing, okay. Or maybe it's F2 of Sn. Right, so if I had a discrete, maybe it's mass 1, maybe it's mass 1.1, maybe it's mass 2. That's sort of the same, same discrete approximation of this, right? So you could call this the multiple worlds view of the world, right? So you'd like to somehow say for any of these robots, I'd like my controller to work. How does that snap into the equation? Well, it's harder, and it's sometimes too much to ask, but it's very natural to say, what if, so I said I want V of F of S to be less than V of S, right? What if I now just say, I want to find a function that satisfies this for V1, for F1, F2, F3, and so on, right? You just add more constraints, saying that for all the instantiations of my model, the robot is the Lyapunov function is still going to go downhill as I proceed.
Does there exist a Lyapunov function for every system, or will it not be solvable sometimes?
If the system is stable, then there will be a Lyapunov function. The way it doesn't necessarily have to have a nice form. That's a great question. Here's the construction that can prove it, okay? Just take the time, so if the system is stable, for any initial state, just simulate it forward till you get to the goal. Take the time it took to get to the goal, and call that your Lyapunov function. Okay, so that's not a computational way to construct it, but that's an existence proof that there's a Lyapunov function. Okay, and now the question that naturally follows is, if the system is stable for F1, F2, F3, does there exist a Lyapunov function which simultaneously proves stability of all of them? No, right? So this is a conservative, this notion of a common Lyapunov function is conservative. Even for linear systems, and I'll do that example once we have semi-definite programming next time. The system could be stable for F1, F2, F3. They all independently have Lyapunov functions that would prove it, but you can't find a common Lyapunov function that would prove it. Even in simple cases, there's counterexamples. Okay, but in practice, it's you get pretty far with some of these ideas. Okay, and they're a really natural way to put it in. It just depends on Yeah, it depends how stable you are. If you're on the brink of stability and you have uncertainty, then you might be hosed. There's another subtle point of your question, and thank you for asking that. So if I'm looking for a finitely parameterized function v, right, that was written of some basis functions, the system could be stable, and I wouldn't be able to prove it with a Lyapunov function of that particular functional form. Right? If I chose some basis functions, for instance, let's take the pendulum, and I said my only basis function is sine theta, it's not going to succeed, right? So that one does come up and bite you in practice experimentally. You'll fail to find a Lyapunov function, and then you start trying to add terms and try to look around, and there's a natural inclination to say, okay, what if I just did degrees up to 3, blah, 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 and then things start getting bad when you start taking terms to high powers and the like. So there's competing interests there, and that does set some of the, you have to set your expectations for the numerical systems to do that. Good. So I think that's actually pretty easy. But the idea that this constraint is linear, right? Because in those constraints, f was given, s was given. So everything I've written today, the reason it's a linear program is because f of s is basically evaluated. It's a double. Okay, so in the code, right, s is given at a particular sample. It's known, so f is known. F could be as complicated as it could be, but this is still just a constant, right? When we start doing control design or something where you have to look inside look inside f, then that no longer becomes true if a is unknown. But in this case, this is still just a set of linear equations, and you just have more linear constraints. It's still a linear program or a quadratic program if you chose to put some nice objective on there. Yeah? That's a really powerful idea. It went by really fast, but I think that's a powerful idea. So that was, that is, I feel, a major limitation of what we said so far in, dynamic programming for swinging up the pendulum, was that we have something that is baked in numerically, very particularly to our model. And in practice, executing that can reveal false dependency, unwarranted dependency on those model parameters. Okay. Any other questions? Yeah.
So do you solve for E in any different way than you do for just one? Like, do you have to make your basis larger? Because this looks a lot harder to solve than just for one.
Right. So there's actually, I have a good example that for linear systems where you can see the geometry of it and everything. I'll bring that next time. I can't do it this time. I couldn't have brought it this time because it needs semi-definite programming, and I decided to wait until next week to do that. But there's a good example of that. In practice, you can try. You could try to see if you could find an energy function that with the same basis function works for multiple masses and the like. You may or may not succeed. It just depends on how big of an ask you made. Yeah.
How do you make the sampling points?
How do I pick the sampling points? Densely. In the low dimensions, this is a straw man, right? So I love the LP version of it because it's clear and it's good to think about. But I don't think it scales to high dimensions because it's hard to pick the sample points in a rigorous way. And I don't actually, by doing it on the sample points, I don't have any guarantees about stability of the continuous system, right? Yeah, I only chose the sample points where I put the mesh on the pendulum, the same sample points, because it helped me explain the ideas with linear programming first. And the sums of squares version hides a lot of the subtleties. So the idea that you have to put boundary conditions on this for it to be well defined, otherwise it goes off to infinity. Should you push down on V? Should you try to match some quadratic objective, which is like your cost to go? All those things are very, very hard to see in the SDP formulation, and they're just right in your face here, very easy to understand. So this is a board value, and low-dimensional systems, it's good. But I hate the samples. It's the Achilles heel. Yeah?
And how far we can go in terms of dimensions? 2, 3?
So I haven't pushed it because, like I said, this is my straw man. I would expect you to do fairly well. Yeah, I don't want to make statements. So people do dynamic programming up to 5 or 6 dimensions, and there's no reason this shouldn't go as high. These are more expensive problems to solve potentially, but Gurobi's really good. I have never tried, so I don't have a concrete answer, but I would expect the dimensionality to be similar, and I would expect the pain points to be the solver start getting slow, and then that just you feel like the resolution of your mesh at higher dimensions no longer represents the continuous system. Okay, please run and see the numbers when they're there. I'll post a note in Piazza, and I'll see you Tuesday.